Hey guys, how are you all? Once again, there's a contest. You know the drill. So, shoot. Actually, this is a bit messed up. I have to recover my old template. Let's pull it from here. Yeah. And then, no, okay. Everything else is good. And we're gonna be ready. And the recording's gonna work, and then everything is gonna be great. Let's go. Welcome to Rockport City. It's time for your first. Yeah, anyway, round 7:30 is now, so that's now. Let's go. To make the race interesting, you have $8 and Ronnie is bet $B. Excitement in the fans. Maximum excitement the fans can get and the number of moves required to achieve it. Okay, it's gonna be related to the difference between the two. So the best you can do is the difference between the two. Suppose the GCD is larger, then like one of them will not be divisible by it because like modulo stuff, both of them mod that difference can't be 0. So the best we can do is the difference between the two, and that is the best we can do. So really we're just looking for the closest divisor of the difference between the two. So that should work. Either we go up, then we spend like the time it takes to go up, or we go down, then we spend X mod D. And I need test cases. Like either we go down and we spend X mod D, or we if D is equal to 0, so yeah. Wait. What? Wait. Ah, okay. Else print D, and then yeah. I'll give a more intuitive proof, or I'll give like a more actual proof in the explanation after the contest. Oh yeah, and the whole point of having this open was to do this. Passes samples. Yep. Because again, the cost for going up is the other thing. D has subtasks. Okay. Last time E had subtasks. And E was hard, so maybe D is hard this time. Highway 201 is the most busy street in Rockport. Traffic cars cause a lot of hindrances. You have an array A, where AI represents the number of traffic cars in the ith subtract. The inconvenience is the sum of the absolute difference. You can choose a traffic car and move it from its current track to any other track. What? So basically you make the numbers as close as possible? Okay. Actually, that's not true. Moving the car from 1 to 1 would make it worse. Which is not good. Oh yeah, decrease. Okay, never mind. That's fine then. Basically, we want them to be as close as possible. Because if not, then like we could move it and then it would be better. It would be closer to the rest of them. So basically we just make them equal to the average, but then like some of them are 1 plus the average because like can't divide them evenly. some more mod stuff. That is a thing that happens with this contest, apparently. Basically, so S is like the number of zeros we have, and then M minus S is the number of ones, is the number of, not zeros and ones, but like some of the numbers are X, which is like the floored average of the array, and then some of them are X plus 1. And this is the number of X, and then the rest of them are X plus 1. Yeah. Seems good. Defeating a blacklist rival, you get a chance to draw 1 reward slip out of X hidden valid slips. It's not interactive. Okay. Oh shoot, I did not mean to click on it. Initially X equals 3, and these hidden valid slips are whatever. C, M, and its probability. Okay, this contest is exciting. C, M, and P. It's also a volatility factor. As long as you don't draw a pink slip. Okay, what is happening with this? Is this the thing that doesn't let me submit? I guess I will do that again. Okay. Took longer than it should have. What is V? Okay, so it reduces this probability. Reducing X by 1. Okay, that's weird. Alright, so because V is between 0.1 and 0.9, everything will be done at most 10 moves, I guess. So we can iterate over C and M. Oh yeah, there is at most 20 moves, so we can theoretically iterate over a bit mask, but like also... Or wait, no, there's almost 40 moves. Because, half of the... Yeah. So when we remove a thing, half of its probability goes to P, and half of it goes to the other one. Okay. So what matters is the number of C's we've had and the number of M's we have. And also we have to make sure it's a valid sequence, but I guess the way to go is some sort of like DP thing. Okay, so we have multi-tests, memset, dp0, size of dp. So basically the dp of like x and y is the probability of picking this many C's and this many M's in general. That's our current state. So for li equals 0, I is less than something. Well, okay. So 0.1, at each move, either C or M loses V over 2. So the number of moves that can be made at most is 40. So we can do like 43 or something. J equals 0, that's 43, J plus plus. So there are 3 things that can happen. So we can take C. Well, actually, let's find, here let's just find the probabilities of the dp. So, LD, so the new probability of C is the old probability of C minus the number of times we've drawn this item, minus I times V, and then maybe we get some back from drawing the other item. So plus J times V over 2. For PM, it's the same thing. M minus J times V, that's the number of probability, that's the amount of probability we lose. And then we get some back from taking I. And then the probability for P, which is, yeah, variable name, is probability of P. It doesn't mean anything else. Is the initial value of P, plus we get something back from taking the I's, plus we get something back from taking the J's. If our probability is close to 0 and we have precision issues, then I think it shouldn't be a big deal, so we don't really need to use an epsilon, because then the probability would be near 0 anyway. Okay, so if PC is less than 0 or PM is less than 0. Alright, no, that's fine actually. Alright, okay, how's this work? So if PC is less than 0, then the rest of it was distributed equally. So then we sort of add it back to PM and PP. Or wait, it was like, yeah, they need to be decreased because they didn't actually get the last V over 2. They got whatever was left from PC. So if PP is less than 0, then if PC is also less than 0, everything goes to, alright, this should be PM. In this case, everything goes to at least we can do some casework. If both of them are less than 0, then the only transition we can do is ants plus equals dpij. That's it. Probability 1, because P is the only option we have left. Otherwise, if only PC is less than 0, then PM plus equals PC over 2, PP plus equals PC over 2. Otherwise, if PM is less than 0, then same thing, we need to like undistribute the extra stuff from PM. So we do this, and then some extra stuff here, and then otherwise neither of them are less than 0. Continue. So then PC is equal to 0, and then PM is equal to 0. Now we do the transitions. So take C. Then here the probability of taking C is PC. So dpi plus 1 j plus equals dpi j times PC. We can take M in the same light times PM. Otherwise, the other option is taking P, and then we add that to the answer because it stops at this position. I already have set precision, everything should be good. Or not. Okay. Why now? We're doing multi-tests. Okay. So let's see. Exactly how far does it get before it dies? Does it just stop at 0, 0? What the hell are you doing? Oh, this has some stuff in it. Oh, wait. No, wait. DP is double. Is anything not double? These are doubles, this is double, these are doubles. I guess that shouldn't be an issue. Actually, that would be a problem if I do that. These don't have to be doubles though, because V is a double already. V over 2 is valid. So in the states where it works, for example here, the probability of this is, so it all comes out to 1. Oh wait, that's why. Because I need to multiply by the actual expected, oh yeah, of course, okay. This tells me the DP is working, because it tells me the sum of probabilities of all outcomes is 1, which is obvious. Something's gonna happen. So the probability of something happening is 1. But we actually need the expected value, which is the number of draws, right? Yeah, expected number of races. So I plus j plus 1, because that's the number of draws it takes to get here. And then this is also I plus j plus 1. Yes, good. Let's get rid of this. Now it should hopefully be correct. 547. It's a bit off. Why is it a bit off? It's just a tiny bit off each time. But it's not like consistent. Like this is lower, this is higher. What the hell is up with that? Okay, so if I is less than 3 and j is less than 3, we're going to debug the first one. So the first one is a bit wrong. 0, 0, probability of being here is 1. Then this. Do I have to do this again now? No, it doesn't fix it. Okay. Alright, so we're debugging these values. So the probability of getting to 0, 1 is... Okay, so they actually do have the cases, which is nice. So P with a probability of 0.6, then CP, so 1, 1 probability of 0.2 times 0.3 times 0.9. Oh, that's a bit wrong. Why is that a bit wrong? So that goes over there. Wait. Let me do this. Still messed up. Okay. Why is this the case? Just a little bit off now. So CMP. Yeah, okay, it's correct. Maybe we just don't use formulas. Is that what we need to do? Maybe the order also matters. It's kind of a thing. I think I'm like... We're gonna need a flag for if we run out of stuff here. Because the order in which we do things does matter. Yeah, it does. Is there a better way to do this? Also, I don't understand what's happening here. Oh, right. Okay. Yeah, it's just wrong. Okay. So let's add 2 more states. Which is saying, have we run out of C and have we run out of P? Or have we run out of C and have we run out of M? Now we need to do some stuff. So now we're messing with this a bit, but it's fine. Now this determines what happens with this. I hope this isn't intended. There's a better solution that doesn't involve this, but I don't really know how. So, let's see, I mean, does it even matter, like, what's what? Like 0.1, 0.15, subtract from here. So that means I'll give away that 0.5. I feel like there's some like it doesn't matter stuff going on, but I don't really know how that works. Okay, now we do some stuff here. So if CV and MV, if we lost both of them, then PC is equal to PM is equal to 0, PP is equal to 1. Else, if only CV, then if only CV, then PM plus equals PC over 2, P plus equals PC over 2. Wait. How much does it matter how much has been given away? Like we give some from, like maybe we give some from M to C and then back to M. And that's different from perhaps like running out. Does DP even work here? I don't know if we can reconstruct the values. My tablet is right here. I don't know where the pen is. So my problem right now is like, we have like 0.15, and then 1, and like whatever's left, 0.75. Then we subtract, and then like V is 0.2. So then this loses everything. So this gets like minus 0.15. This gets 0.175. This gets 0.825. Then we get rid of this, and that gets everything. And that's fine, actually. But if we do it like backwards. I don't know if it matters. That's the thing. But I also feel like it does. We can't just iterate over masks, because that's too much. There can be up to like 39 moves, for example. Right, because with 0.9, there can be almost each move can wait, what am I saying? Oh no, I'm being dumb. Okay, nope, we can just iterate over the moves. I don't know what I'm doing. I don't know what I'm doing. Yep, this is all dumb. I genuinely thought that C plus M could be greater than 1. Nope, we can just iterate over the moves. Yep, let's just iterate over the moves and be done. Alright, now for j is equal to 0, j is less than. We also need to keep track of it as possible. Yep, because v is at most 0.1, I'm just being dumb. Why do I do this? J is less than 20. J plus plus. So any move sequence is at most length 20. Yep, they did it specifically for that. And I still missed it somehow because I thought it was. I thought C plus M could be greater than 1. I don't know how that happened. Let's see. Also, we don't necessarily have to work with. I don't know, maybe we do. Okay, so actually we can iterate over the length too. I is less than 21, I plus plus. Then we can do j is 0, j is less than 2 to the I, j plus plus. And then this sums to 2 to the 22nd. And then for k equals 0, k is less than I, k plus plus. Then we're iterating over the length of the sequence. So if j shift k and 1, then we remove from C. So prob times equals cc. Actually, we can do some trick here. Basically, we treat it like we're always taking from CC, and then if not, we swap the two so that like the CM becomes CC and CC becomes CM, that variable. So like we can just do it once and not have to copy paste the same thing twice. But yeah, CC is like the current C again, CM is the current M. So if CM is greater than EPS, it's equal to the minimum of V and CC. CC minus equals D. Prob times the probability of doing this is CC. Then CM is greater than 0. Then CM plus equals D over 2. CP plus equals D over 2. Else, it all goes to P. I plus 1 times CP times prob. That was a lot of wasted time. How slow is it? For example, if we do like 10 0.5, 0.5, 0.1. Then we repeat that case. What the hell did I just do? I just download the page. This is the worst case, so if this runs in time, then we're fine. Oh, it might not actually. I don't know. 2.5 cents. Oh my god. Well, the longest length is actually 20. I guess we can do that. Wait, does it change the answer? Makes it faster. Still not fast enough, actually. Suppose we have that. We do it twice. We do it twice. Reduce it to 0.45. I don't understand what to do with this problem. Are submissions running like... I don't get it. And we have this and it speeds it up. Oh wait, that's why. CC is equal to 0. No, never mind. That's not necessary. Get 10 to the negative 6. I guess that's fine. Does this work fine if we do this? Yeah. Problem I'm seeing is specifically this case. If we iterate only up to 20, it changes the answer. Right? Like if we iterate only up to 20. Answer was this, and now it's this. If we iterate up to 22, it should not change the answer anymore. Right? What? Wait. How is this changing the answer? Does that mean something's messed up here? Or am I messed up again? we're at the point of 1. Maybe it's less than that length, actually. What if you just do like a DFS, then it'll work? Is that what they want us to do? I'll be fast in iterating over masks. So, alright, so now we're doing this again. CV. C minus equals D. M plus equals D over 2. P plus equals D over 2. Else P plus equals D. Prob times equals C. So then it's plus equals prob times P. That's the chance that this is the last move. Okay, now FST PV prob 0 def plus 1. Just don't understand. CMPV 1 0 0. Same thing for move 1. Is this faster? Am I worrying about time for nothing? I mean, it took like a lot of time on that case. This is the thing. Void. Why is it off at 1? See, I'm also missing this case. This is the probability. With probability P, we do nothing. Now this should be depth plus 2. And answer equals P here. Okay, now is this fast enough? I know it's like technically not the case, because this can't be 0, but it can be like 0.0001 or something, and that would, I guess the move sequence is at most like 19. Is this the answer? Oh, wait. 0.1. Yeah, that would end it quickly. Okay, whatever. That's fast enough. I trust it. If I get wrong answer, screw it, I'm done. Tired of this problem. Do get wrong answer. Okay. How does this happen then? Is it epsilon issues or is it something dumb? If I set the epsilon to 0, what happens? Okay, actually, what if we just got rid of doubles entirely? What if we just did that? Maybe that would make everything better. Well, wait, no, we can't. Not with probabilities. I guess the probability can be that. Because we have at most like this many decimal places. So if I multiply everything by like so, okay. Does this still work? Is the point to convert it to integers? No. Okay. Awesome. Why is this the case now? Let's do what I want. Okay. Hopefully this is enough. I mean, everything's integers now except for this. So if the logic is wrong, that's a different issue, I guess. Okay. So it's precision. Alright, I'm going... Alright, I can just read this. So k equals 2, k is at most 100. It's interactive. K at y is XOR equal to the new number. Yeah. So this is bitwise. Okay, so with bitwise, it's easy to check. Yeah, with bitwise, you just check everything and see how the answer changes. So that's simple. I guess we can code this right now. Cn to n to k. So for LO, show you the value is at most what? Yeah, 0 and n minus 1. Okay. So I is equal to 0, I is less than n, I plus plus. Cout I XOR x and del. Cn to y. Are there multitests? There are multitests. So if y is equal to 1, return. So let's say n equals 4. The hidden number is 2, or hidden number is 3. So I guess 0. Now I give you 0. And I guess 1. Now I give you 0. So now the number is 2. Oh, wait. So 0, 0, 0. And then, yeah. This part should be fine. And I should have done this earlier. I don't know why I didn't just try and moving past C. Or what? Huh. Why? Let the current password be X. Oh, wait. Okay, it has to be the number I guessed. Pretest 2. Okay. I'm going to the bathroom. I'll be back. Okay, there's almost 100 here. I guess that's more interesting. Still good? Okay. I don't really understand why the hard version is harder either. Why is the hard version harder? Isn't the number just uniquely determined? So instead of XOR, we just like do it better. Oh, KX. So like while mod K, KB is equal to B mod K. So X XOR K is Z is equal to Y. So it's like basically X plus Z equals Y mod K. So we know X, we know Y, we need Z, so Z is equal to Y minus X mod K. I don't understand what the issue is. I don't even need this actually. Actually wait, yeah, maybe I do. C plus equals R times K, KA plus KB mod K. So R times equals K, A divided by K, B divided by K. So A is equal to I, B is equal to KX, IX. So Y is greater than 0, B is greater than 0. Basically, we need B minus A. So KA is equal to A mod K, KB is equal to B mod K. C plus equals R times, so it's KB minus KA plus K mod K, plus K to like make it positive. I really don't understand what the problem is here. So 4, 2 should give the same order. X. Should give the same order. So 1, 4, 2. No. Okay, something's messed up there. A is greater than 0 or B is greater than 0. Huh? Is it weird? Is it weird the way it works? Do we need like parity stuff? Is that the thing? So Z is essentially equal to Y minus X. Oh, yeah. Z is Y minus X. So wait. So after one iteration, you get essentially y minus x. After two iterations, you get like an alternating series, basically. After two iterations, x becomes whatever the other password was. So suppose you guess 0. You start the guess with 0. Then z is equal to y minus x. So you just get negative x. So now for the second guess, we should invert all those things. So because k is almost 100, we could theoretically just iterate over every value and see how it would change. I guess that would work. So every query we make, we iterate over the like potential things, and then we look at what would happen to each of them. And then we want to figure out what if the password was initially I, then we construct the answer from there. Okay, I guess that would work. Just call it what? I don't know. Basically taking the log. Actually, wait, it's just n, right? Yeah, there's no reason to need more. So I guess that's fine. So we take log base k of n. So we only need like that many. Okay, now for loj equals 0, j is less than size, j plus plus. So for loj is 0, j is in size, j plus plus. We're essentially asking CV is equal to V mod K. And then at the end, we do CV divide by K, or V divide by K. Extracting the current kit of whatever the number is. So then R is equal to 1. So then G plus equals R times whatever the new kit should be, which is what for this and then CV. So, now what? G mod K. Then the new what is again y minus x. So what JCV is equal to y, which is, that is this guess. And then we iterate over the new digit. We iterate over whatever this digit was before. So if this digit was previously x, then now it's CV minus what JX plus K mod K. I'm not gonna do mod. I guess we have to anyway. I need to do it here and put it outside this loop. So for j up to size, we take the current like digit, then we say for iterating values from 0 to k, we take this old value and now it will be our guess minus that mod k. Yeah. So what again is asking, if this digit was initially whatever the digit is for our current guess, then what does it become now? And we need to trace this array. 4, 2. Huh. Cout size 1, 4, 2. Oh, it does get 0. No, it doesn't. What? Oh, because I'm not printing anything. Cout G and O. 0, 0, 0, 0. Awesome. Okay, what the hell? Oh, actually, that does matter. So for LL, I equals 0, I is less than 25, I plus plus. 0, j is less than k, j plus plus. What I j is equal to j. 0, 0, 0, 0. 5. How are you 5? What even is size? Oh wait. It should be n minus 1. 1, 4, 2. Okay, still messed up. Awesome, still messed up. No, clarification doesn't matter. So this part seems fine. Now for each thing up to size, take the current guess. This is how our guess affects us. The old password is x, now it's z. So z is y minus x, y being the guess. Oh, that's why. Yeah, not many room for typos, I guess. So it should be my printing size. Yeah, okay. let's not do that. It would be nice if they had us like put a question mark or something that would distinguish it. Why are you 1? Why are you 1? Why are you 1? What is the point of you being 1? Initially it's 3. Oh, actually that was right, wasn't it? I don't know what this is. Not that. I copied the sample instead of my own code. I don't know what I'm doing with my life. 1, 4, 2. This is 0, 1, 3. Wow, okay, that is correct. Okay, good. So I guess we can manually evaluate. Let's do 6 and 3. And then suppose the password is 0, 1, 2, 3, 4, or 5. So we guessed 0. So 6 is specifically 20 in base 3. So we guessed 0. Now, supposing it is 0, it would be 20. So after the first guess, everything is as expected. Or right now. After the first guess, everything is as expected. 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2. Now, after we guess 0, what happens here? So in particular, we don't care about this because we already guessed this. Now, what happens to this after we guess 0? So this should become 0, 2. Should become 0, 2, should become 0, 1, 2, 0, 2, 2, 2, 1. Now we guess 1. Or now, in particular, we guess this. Which means that now it should be, this should still be inverted, so this should be 0, 1, 1, 1. And everything before should be 2 minus this. So it should be 1, 2, 0, 1. Now everything again gets inverted, so we have 2, 2, 2. And then it should be 1 minus this, so 1 minus 2 is negative 1, which is 2. 1 minus 0 is 1, this is 0. Now this, now we get 2 minus everything, so we get 0, 0, 0, and no, 1 and 2. Then we do this, now we get 0 and 2. So if I'm correct, then this should be what we guess. 1, 6, 3. So we guess 0. Now we should guess 2. Now we should guess 1. Now we should guess 8. Now we should guess 1. Now we should guess 2. Perfect. Okay, and I think that works everywhere. Cool. I'm gonna hope it doesn't time out. I think it should be fine. But I don't know. Maybe it TLEs. I think the problem is mostly printing a lot of output. Or wait, I don't really know. I mean, there is a lot of output. Gets through pretest 2. There are only 3 pretests on this? Jeez. I don't like that. Let's see how we do. Maybe TLE? It's possible. Anyway, what's E? I haven't even followed the statements. Okay, pretest 5. I guess it took a while in pretest 4. I don't know. Pretest 7. Okay. Permute n-dimensional hypercube. Oh, 1310. Okay, we're totally fine. What the hell is this? 16 cubed. So this is their anti-AK problem, huh? Alright, how are we doing here? Okay, C is actually hard. C is surprisingly, like, actually hard. What the hell? People are actually not solving C, which is crazy. Like, all the top people don't have, that's crazy. Wow. Okay, I feel less bad about doing so bad on this now, Jesus. Oh my god, people did so bad. Okay, well this is not bad anymore. We're fine. We're fine. We're fine. We're fine. How do I have such a point advantage over Gabe? I guess it's that problem, and then... Oh, you messed up A. I see. Alright, so this was just implementation that took a while because everything's taking me a while because I'm tired. So, now E. Let's actually read the problem. Give it a chance. Finally, you defeated Razor, and now you're the most wanted street racer. Okay. A permuted n-dimensional hypercube. Take two simple n-1 dimensional hypercubes. I and I. Okay, I guess that makes sense. So it's a graph, except that like it's like a cube, and they can't visualize a 4D one because why not? Color. Huh? Oh. How does this work? Rotation uses 5, 3. Oh, okay. Oh god. Okay, so every vertex has the same degree. Every vertex has degree n, right? Yeah, every vertex has degree n. So basically we just need to deconstruct the hypercube. Every vertex has degree n. Every vertex has degree n. Does that mean coloring is easy? I don't know what the point of the coloring is then. Like, we should just be able to do greedy coloring, right? Oh my god. Now, is there not a color? So we do 0. 1, 1, 1. Is 0? Oh, I guess it's harder than that. Like, for example, 0, 2. 0, 0, 1, 2. Now this gets 1. Now this must be 0. Yeah, so this must be the same color as this, right? Interesting. It's so weird. Okay. wonder how hard is it to find a permutation? So for every edge, there exists an edge to every other number that is the same but with a flipped bit. So like coloring and permutation seem completely independent. We find the hypercube. We find the permutation that gives us the hypercube. Now we need to color a hypercube. So like, is this just a thing? On the hypercube coloring problem. And it's shown that x2 of n is approximately n. Distance k from each other. Different. Chromatic number. Well, that's not necessarily true. That's not the type of coloring we want. We want a different coloring. Only coloring such that... So like for the first vertex, we can color arbitrarily. What if they intentionally made it hard to visualize just to like screw us over? Right, so like we get a lot of edges. And I can try to figure out some things. What are we figuring out exactly? This is such a weird problem. What are they doing? Is this just like intended to be like intimidating for Duke 2 participants? Which includes me, by the way. It's having that effect. But is that the point of this problem? Color the vertices for every vertex U, for every color C. Okay, so suppose we have like okay, we're putting down chains. Putting up 1 here, and 0, 1, 2. And yeah, this is supposed to be next to 2. How do we find the permutation? Let's start at whatever 0 is. Rotate so like 0 is the start. Now we have n edges. Rotate so 0 is the start. Maybe 1 is like part of the solution to the other, or something. Rotate so that 0 is at the start. Now we have n There are n edges that represent flipping the first bit. There are n edges that represent flipping the second bit, etc. The first, the second. Character edges. We can also determine the structure of whatever we're doing. So we have a hypercube here. Now we sort of like branch out. Now in the second vertex, in some other vertex, the only common link they have is that. All the others are totally irrelevant. Those things are totally irrelevant. How much time do we have? 45 minutes. Okay, so it was 12:50. Oh, okay, it's 2 hours and 15 minutes. Fine. So there are only like 16 possible graphs that we might have to color. Can we color like different one? Like for this, because there's no coloring, what does that mean? We start at 0. 0 is an edge to 1, an edge to 5, and an edge to 7. Now we haven't really assigned any meaning to what these edges are. Well, you can find... it doesn't matter. So maybe like build it up recursively from 0. So we start with 0. Now we find any edge from 0 to anything else. Now from that edge, we need to find some other, like, one-dimensional hypercube that works. There's a fly here, like buzzing around. I don't know if it's audible. So basically we need to find another edge such that there's an edge from 0 to that edge, and there's an edge from 1 to that edge. How do we do that? So we look at all of 0's edges, we look at all of 1's edges. They don't have any edges in common. If they did, that would be weird. So because they don't have any edges in common, what exactly can we do here? Given the order somehow? So there's that. And this, we look at the edges of 0, we look at the edges of 1. 0 and 1 are guaranteed to have some neighbor, or there's some adjacent edge that works. Now we look at the next. We look at 1 and 1. Find two, we have to find the neighbor of 0 and the neighbor of 1 such that they're adjacent to each other. This is not that bad. Look at the neighbors of this. Exactly one of these neighbors. Suppose multiple are, then it must be equal. Okay. 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 So look at the current component. Now we can really pretty much do anything. Right? Okay. I think that gives us how to do the permutation. Basically, we construct it like dimension by dimension. We start with 0. Then we pick a neighbor of 0. We construct the 0-dimensional hypercube for that, and then we merge those two together. Now, we construct it for 1. We construct the 1-dimension. So we pick another neighbor of 0. Then the other neighbor of 0 must be adjacent to 1. And therefore, we will construct the 1-dimensional hypercube for the neighbor of 0, and then some other neighbor of 1. Noting that every vertex has at most one neighbor that's in the relevant component. Right? Noting that every vertex has at most one neighbor in the relevant component. Because if it had more than one, it wouldn't be possible. Then it would have to be like equal to one of those numbers. Yeah, okay. I believe it. Don't have a solid intuition of it, but I believe it. Essentially, we construct the neighbor. Okay. We start with this. We construct the 1-dimensional hypercube using only the neighbors of this current hypercube. And that way, because it's true, then the construction works. Now all these are important. Now we just pick another neighbor of 0, and we rinse and repeat. Possible for a neighbor of 0 to be neighbor of a neighbor of 0? I don't think so. Yeah, then again it would have to be 0. That's in this neighborhood. What differs from 0 by this bit? So if it doesn't have this bit, then it doesn't have this bit, and therefore it's in that neighborhood. Yeah, okay. How do we color it? So we have 2 hypercubes like that. So can we color a 4D hypercube? If it's like, if n is greater than 2, print -1, it would be dumb. I'm assuming it's not. Maybe the idea of merging hypercubes can give us something? Well, right, suppose we have 2 hypercubes that are... Suppose we have 2 hypercubes that work like that. And we merge those 2 together. Now that edge must be... Oh wait, suppose we have 2 hypercubes. Okay. Now, merging hypercubes can add at most 1 edge. So therefore, we must have perfectly colored hypercubes to be able to merge into another perfectly colored hypercube. And there's no way to perfectly color a hypercube of size 3, which the problem tells us. So because of that, I don't think we can perfectly color any other hypercube either. Because we're merging 2 hypercubes. Those 2 hypercubes must be perfectly colored. Because the merge only adds at most 1 edge to every node. Okay, so that basically gives us everything. Vector, L, edges, okay. 4, Cn, edges, I.clear. If n is greater than or equal to 3, C out -1, else we're coloring specifically that permutation. Okay, so for 0, 0 is part of our set. Okay, now So let's see, if n is 1, otherwise n is 2, so it's a square. So we just need to C0 is equal to 1, C edges 0, 0 is equal to 1. Okay, now test the coloring. Alright, now we have one thing left, we just need to merge the hypercubes. How do we do that? So we start off solving for 0. So 0 is base case. Now the importance set is specifically 0. So we pick some neighbor 0, we solve for that with the importance set being 0. We add that to the importance set, add 1 to that. Now we pick another neighbor 0, we solve for that with respect to the importance set. Everything works. Okay. Rule this for Li equals 0 is an m, I plus, this I is equal to 0. So right, okay. So for Lx edges 0. Void rec if I do this, it's linear time. Okay, that's fine. Rec, so it's LB, LL depth. Vector LR is equal to rec, edges 0, I, and the depth would be I. Now, for LXR, this x is equal to 1, AX plus equals to the I. Now, with here, so if d is equal to 0, return vector LL1V. A is equal to rec otherwise, okay, for I is equal to 0, I is less than n I plus plus. Only if visited let's see. Not visited edges vi, and it's adjacent, then we need to construct the thing of size c with respect to that vertex. Right, we need to construct the thing of size c. With respect to this vertex. Return x. It's going to be bar. Is rec so recursion here. So we might as well say this is visited now. And everything next to me is adjacent. Oh, right, okay. How does this work? So here we have this, merging this. Okay, we'll make this edge. Edge I is equal to 4. I'm confused about how this works. This needs to be adjacent to this, and it needs to be adjacent to this. going to be adjacent for this. Then we're solving for this. Then we're solving for this. And within that... Oh, right, okay. This makes sense. One. Do like plus plus. So now we're going here. So it shouldn't be 2. It should be specifically the requirement plus 1. Then we recurse into that vertex with the depth of C and the requirement plus 1. R is equal to merge R OB. Is that enough? We don't need to do this. Now here we're essentially saying this becomes adjacent to one more important vertex. Yeah. Okay. For A I don't trust it in the slightest. Epic. Okay, why? 1101. Oh, wait. Okay. Don't need to minus there. Cool. I'm reading multi-tests. Yeah. FST C into N. What's happening here? Oh, 01, 02. Okay, so that's just messed up. Okay, so So we're starting with 0. We really don't need to like do this weird like initial thing. Let's start with 0. Initially here. Yeah, I don't even think we need to. I think we can just like. Okay, so rec 0 n1. Right, so this v is equal to 1. So 0, step 2, 1. Oh, it should not be rec plus 1 anymore, it should just be rec. Okay, 01, 02. So we're recursing for 0, 2, and 1. And we look at the edges. First we get to 1. Well, okay, wait. First, I think we can do something here. So for LOX edges I plus edge x. Okay. Now we can do it like that. Now we iterate over here. We find the recursion. We return. Yeah. Just v. Okay, that's good. Nope. Okay. So that's wrong. Alright, now let's see what's happening. So visit v equals 1. Now for each edge, we increase the number of adjacent things it's adjacent to. Now, if this is the end of the line, then just return that vector. Otherwise, for each adjacent edge, if that edge has not been visited, and its adjacencies work out, specifically it's adjacent to everything we want it to be, then we merge in there, right, that component, then we're here. R equals merge R of V for each x. Ax plus equals 2 to the c. Okay, let's see how we're recursing here. How does this work? What if we pass the value like so? are we doing that? M plus 2C. A, B is equal to M. Oh, 1, 5, 2, 7, 3, 4, 6. If I swap these two, is it fine? No, it is not fine. Shoot. 0, 1, 5, 2. Why is that messed up? Why is that messed up and everything else works? Okay, so for each adjacent thing, if its adjacency is equal to the number we need, then go there, and it's not been visited. Then go there, rec edges bi, c, rec plus 1, requirement plus 1, and then m plus that. So what order are we visiting vertices in? So we're merging. Oh wait, it needs to be done. Specifically like this, doesn't it? Yeah, it does. We could determine something priority. How do you determine the priority? We find like the that has to correspond to the right one here. Okay, yeah, this is good. I'm glad we caught this because this would mess things up. So we built this hypercube. Now we need to recurse into the next one. But before we do that, we need to explicitly set the order in which we visit things. Right? We tag each of those. Okay, I got it. So tag is like the smallest vertex. Tag I is equal to only 9. Right, okay, so tag x equal to mint tag x v. No, it should be m. Okay, now sort edges v. Now it should work. Specifically because now, when we build this, now we're pushing everything over to that. Now it needs to be visited in specifically this order. And that's the way we do that. Do it like that, then we visit that one, then we visit that one, then we visit that one, etc. Okay. Because we have 5 minutes left, I believe in it. Alright, now I need one more test. Actually, first let's make sure we're doing everything right. Clearing edges, resetting everything. Yes, okay. So we need 1, 2. And basically just need like a singular case where it doesn't work to color the first two. So we have 0, 2, 0, 3, 1, 2, 1, 3. Perfect. 0, 2, 0, 3. So 0 can be that. 1, 2, 1, 3. So 0, 2, 3, 1. Okay. Alright, I'm trusting it. I believe in it. I think it can be done. Okay, let's scour for bugs in the meantime. Scene to n. We take 2 to the n. For each up to m, edges I.clear. For each that, we also reset visited, adjacent, and the tags. That's pretest 2. That's a good sign. Okay. We reset that and the tags. Visited 0 is 1. That isn't necessary, but it doesn't matter. Wrong answer, pretest 4. Okay. Visited 0 is 1. Doesn't matter. So we're recursing in this vertex, in this depth, with this requirement up to m. Okay, so we set a v equal to that mask, and we set visited v equal to 1. Now for each edge, add to its adjacency list, and set its tag to the middle of that and this mask. It's adjacent to a thing with this mask. We built this hypercube up. Okay. Now we go down here. We're going to go up to here. This tag works out. We set all these to 2. This is tag 1, so let's go this way. And we built up this whole hypercube. We tagged everything relevant. Now we continue on. Now we build this up. We're going from the adjacencies to 0. We're going to here. Let's get rid of this. Don't need adjacencies. I think we just don't need them at all. Don't need adjacencies. Tag edges vi is less than 28. These are all tags here. Just vi, so we don't need this anymore. Come on, load! Oh my god, are you serious? Dude, I swear to god, if that was right. Swear to god if that was right. What have I done? Oh my god. How do you solve this? Can I see submissions? Why is it not let me see submissions here? I'm mad. I'm mad at that. Get wrong answer 4. Pretest 2. TLE. Interesting. I really, really, really hope that wasn't it. Wait, there's more conditions for coloring? And color if n is a power of 2. Why is that true? You merge 2 3-dimensional hypercubes. Well, like 3-dimensional hypercubes aren't colorful. Three-dimensional hypercubes aren't colorable. So how does it work? Take 2 3-dimensional hypercubes. There's no way to color it. No way. Oh wait, that's wrong because we got right. So why is a 4D hypercube colorable? Why exactly does that work? You have 4 colors, or you have 8 colors. Is it because it's divisible by 8? Why is that the case? Head hurts. We color that like so. Can it be mod? I don't know if it can. I don't think it can. I don't know what it has to do with that. Not coding. What else is the thing? That would work. I don't get how you derive that. System tester happening. Nice, my rank goes up because I solved A slowly. The website correct? Well, that's awesome. Okay, let me try and remember what A was then. Can I even load it? It does. Okay, well, I guess that is the solution to E, whatever that was. So you color it with XOR. Essentially. Am I seriously not able to see it again? Alright, it's just slow. So you can color 4 for whatever reason. I mean, okay, well, why does doesn't it work for the other ones then? Like, why is it that there's no such coloring? I don't know. Alright. Well, I guess that's it. That's the contest. Woohoo. Horrible C, and then just messed up E. A lot of people have like wrong answers on this. How much time did this take? Fine on time, right? Yeah. It's just the only thing was that color. Well, we're just gonna do this. I have no answer for E. All I know is the solution, apparently. No answer for why it's the solution. Problem A. Essentially, you have two numbers, A and B. In one move, you can either increase A and B by 1 simultaneously, or decrease A and B by 1 simultaneously. Now, what you want to do is you want to maximize the greatest common divisor of A and B. That is, it's the greatest x such that x is the divisor of A and x is the divisor of B. So the way this works is, and we also want to do it in the minimum number of operations. An operation is either an increase or a decrease. Values are up to 10 to the 18th because why not? So yeah. Now the basic idea is that's happening. That's going on outside. Alright, so we're basically considering the difference between A and B. So take the absolute value of A minus B. Suppose like we brought it down to 0. Suppose without loss of generality, A is less than B. If not, you can swap them and then you can have that. So, because the order of the numbers doesn't matter, A and B are sort of like the same, kind of. They're treated the same. Every operation affects both of them in the same way. So assume A is less than or equal to B. Now bring it down to 0, so you get 0 and b minus a. Then the GCD you get is b minus a. And the question is, can you do better than this? And the answer is just no. And the reason is because, so let this value d be the difference between the two, b minus a. So then if you bring it down to 0, you would get 0 and d. And you can't do better, because suppose that there was some number x that's greater than d, such that a mod x is equal to 0, and b mod x is equal to 0. So now note that b is simply a plus d. So a mod x is equal to 0, and a plus d mod x is equal to 0. Okay, now this is fine. We can have this be true, and this has to be true. So now suppose a mod x is equal to 0. Then what about a plus d mod x? Well, we can use modular arithmetic rules to say it's a mod x plus d mod x is equal to, and then all that mod x is equal to 0. But we just said this is 0. So really we're just left with d mod x is equal to 0. But that's not possible, because we said x is greater than d. And it's not possible for, like, if you have d mod x and d is less than x, the mod isn't going to do anything. So because if d is already 0, then, like, fine. But otherwise, there's nothing you can do. Actually, suppose d is not 0. If d is 0, it's a special case. If not, then there's nothing you can do. X is greater than d, you can't do better. If d happens to be equal to 0, then this is the case where you can get, like, infinitely large, so that's fine. But yeah, so basically what I'm saying is you can't do better than this. That's what this proof is. And we're sort of just playing a bit with modular arithmetic, and it turns out that this is never possible. So it's a contradiction, and therefore, like, we can't do anything. So d is the best we can do. Note that there is the special case where a equals b, then no matter what we do, the GCD will be equal to whatever the numbers are. So we print 0 and 0, like the statement tells us to. Otherwise, a is not equal to b, so then we do this stuff, and we also figure out, now, that gives us the maximum answer, it's d. And we can always achieve d, we just bring it down, we bring the numbers down to 0 and d. But can we do better in terms of operations? Now what about minimum operations? So we're essentially saying we need a to be a multiple of d. And we need b to be a multiple of d. But because b is equal to a plus d once again, a mod d is equal to b mod d. So really we're just working with one number. We just need a mod d is equal to 0. So imagine like a number line where there's some number a, and then there's some number x times d on one side of a. Like it's the closest multiple of d that's less than a, or less than or equal to a. And then similarly on the other side we have x plus 1 times d. This x, now how much does it take to go down here? Well, the remainder here is essentially the remainder of division of a over d. So this size is equal to a mod d, right? Because if we have a current value of a mod d and we need to bring it down, we can subtract 1 that many times, and that's the number of times it takes us to get to 0. Or we can go up, and the distance here, because we know this gap is d, then the distance here is everything that's not this part of a mod d. So this is this d minus this a mod d, and this is the other cost. So the answer then is the minimum of these two. Right. So that's the number of operations. So within the code, we're first taking the absolute difference of A and B. So I'd use X and Y, but it's the same thing. We take the absolute difference. Then if this difference is 0, then the answer is automatically 0, 0. Otherwise, this value is the GCD, and then the difference is just this. It's the minimum of these two. And then that gets accepted. So it's right. Unless the test cases are very bad, but I doubt it. So that's A. Alright, B is going to be fun to prove. I don't know, it's kind of annoying to prove. Okay. Essentially, we have some values like 1, 2, 3, 5, I don't know. And they're not necessarily sorted, but like whatever. So basically, the cost of this value is for each pair, we take the absolute difference. So this is, for example, absolute difference of 2 minus 1. This is absolute difference of 2 minus 3, etc. And then the answer is the sum of the costs of all of these, the sum of the absolute differences of all of the pairs, like we can get from the array. So in this case, it's like, I don't know, it's a lot. We want to minimize this total cost. And what we can do is, in one operation, we can pick two numbers, we can subtract one from one of them, and add one to the other one. So for example, here we would get 2, 2, 3, and 4. And we want to do it in such a way that minimizes the amount of values we have. So the essential one-liner idea here is that we want to bring them all to the average. Okay, so let S is equal to the sum of all AI. Like it's just 1 plus 2 plus 3 plus 5, which is 11. Then let the average rounded down be X, because I don't know, variable names, which is equal to the floor value of S over N. It's simply S divided by N rounded down. That's what floor is. Because again, because to rehash the average, not to rehash, to review, the average is the sum over the number of elements. So this is just definition of average. So now what do we do? Essentially, some of these numbers are going to be X, and some of them are going to be X plus 1. In this case, we have X, X plus 1, X plus 1, X plus 1. So for example, here the average is 2. So now, suppose there's a number, and how many, first let's just start with this. How many X plus 1s do we have? Well, it's the number of, if we make all of them X, then we have some left over. So, in particular, when we make all of them X, we have this much left over that we have to distribute. Oh, and also you can prove that, with these operations, you can distribute the numbers however you want. Yeah. Yeah. Right? I mean, yeah. Or in particular, you can always distribute them in this way, which is fine. Suppose we made them all X, then we'd have this much left over, so we need to give these ones over. And by the unproven answer and by the claim that I haven't proven yet, it's best to, give these ones, equally. So, nothing gets more than 1. Also, this is definition-wise, it's S mod N. That's the amount of extra stuff we have. So, why is this the case? And the reason is, we can prove that if it's not the case, then we can do better. Okay, suppose we have a number that's too small. So, for example, here we could have, 2, 3, 3, 3. But instead we don't. Instead, maybe one of these 3s, so we don't have 3 3s. Instead, maybe we have a 2 instead. So we have a 2, a 2, a 3, and then 1. Well, the remaining number, we have to have some number that's larger than 3, because otherwise there wouldn't be, like, the sum wouldn't be s. So some number, if some number is too small, then some other number is too high. So consider this too high number. If we bring it down by 1, then it will decrease its absolute value with everything. Like just everything. Or suppose we have multiple too high values, then we can do the same argument, but we decrease all of them at once. Then it decreases the absolute value with everything. In particular, more than half of the array. Since if it's greater than the average, then it's greater than or equal to at least n over 2 elements. Which is like sort of also something I'm not going to prove, but it should be intuitive, right? Like if it's big, like you can't have more than n over 2 things that are bigger than the average. Wait, yes you can. Am I saying that right? I don't think I'm saying that right. No. Actually, no. This proof is dumb. Ignore that. But is it true actually? No, it should not be true. Yeah. Anyway, the point is, if we bring everything larger than the average down by 1, and everything smaller than the average down by 1, then they'll all get sort of closer to each other. Yeah, and we can do that. I don't know, this proof is falling apart. Okay, wait. I think there's a better way to do this. Like the basic idea is like sort of intuitively you can bring these elements closer together and then it will be better. But it's not like a formal proof, but it's sort of like intuition. Like you can bring the 2 elements together, they'll be closer together, the rest of the cost like won't change that much. Or it won't be that much worse. I think maybe we can try some other trick. Another trick with problems like these is like trying to get a lower bound on the answer, for example. Like we find some value such that we can show that the answer has to be at least this value. For example, the lower bound is 0, which is dumb and usually not the case, but sometimes that helps. And so in this case, what kind of lower bound can we get? Actually, I don't know. Maybe there's a way. Yeah, there could be a way to lower bound the answer like that. Sometimes it works, sometimes it doesn't. That is also a thing. Sometimes things cannot work, and then they're not working, and then you're left with a video where you don't even know what you're talking about. You ever been in that situation? Give me a second. If nothing else, just have this idea that if you bring them closer together, it'll make the answer better. Genuinely don't know. How do you prove this? Why are these problems like this? I was like so, like, I know how to figure out, but like, figuring them out is like, you know, like proving stuff. It's pretty hard. I don't know. I think I'm just going to leave it. Basically, you have these numbers. These are the best numbers. If you have bigger numbers that are like more different from each other, then they'll be worse because they're just like farther apart, and you can bring them closer together and they'll be better. There's probably some like operation-based thing you can do to prove that like the answer won't be worse if you do some operation and it works and it brings them closer together. And then you do that operation an infinite number of times, and eventually you're left with this configuration. But I don't know how to figure that out. So instead, we're just going to say, this is our answer. We have, it's always best to do it like this. So we have S mod n x's, and the rest is simply everything else, so it's n minus s mod n of the x minus 1s. So what's the answer? Well, every x has a contribution of 0 with every other s, or with every other x. And every x plus 1 has a contribution of 0 with every other x plus 1. And every x has a contribution of 1 with every x plus 1. So the answer is this times this. So the answer really is s mod n times n minus that. Which is kind of interesting. Because in A, we had like the minimum of something that looked like this, and now in B, we have the product. I wonder how that was intended. But yeah, okay, that's going to be it. That's that for that. Did FST C? See that happening? No, I don't even know, because it took me so long. My thing is so far back in queue. Okay, sorry. That's the best I got. You bring them like that, you figure out their sum. And then you use the average. See, I took 50 minutes on this. We're like 43 minutes on that. So, I don't have words about this problem. I don't have words about it, but yeah. It's not bad, I guess. I mean, I don't know. It's probability. So, I think this statement is convoluted enough that I shouldn't be going over statements anymore. So I'll just do the explanation. So if you pick P, you're done. So suppose you pick C or M. The important constraint here is that V is greater than or equal to 0.1, which means that if you pick C or M, half of that might go to the other one, but half of it automatically goes to P, which is at least V over 2. No, not at least, but it's like basically V over 2, which is at least 0.05. So because C plus M is less than 1, and every operation brings you down 0.05, the maximum number of operations you can do is less than 1 over 0.05 is equal to 20. So the number of operations you do before you're forced to take P, that is, before both C and M are invalid, is less than 20. So because it's less than 20, we can do brute force. And there are a lot of ways to do brute force. I eventually settled on DFS because bitmaps were screwing me over. So, yeah. Because there are 10 test cases, it's like 2 to the 19th. It's like not that great. I don't know, it's 1 second. I don't really know what they wanted, but I don't know what they wanted. So, yeah. Essentially, we're literally just brute forcing what happens. So we start off with no operations. Then maybe we do a C, which has some probability of happening. Suppose this has probability X of happening. Or suppose it has probability like A, like P1. Well, technically it has probability at whatever this C is. But like, suppose this operation is C. So now, if it's possible, then we do it. If it's not possible, like if the probability is 0 or something, then don't worry about it. And also invalid can be represented with probability 0, so that's fine. So now maybe we go C again. So the probability of reaching here is P1. So now we go C again, so now we have P2, for example. And then we so on until eventually it's impossible, and then we return back up here to this state. So now from this state we try doing M, which has probability like P3 or something. I'm just using random numbers here. And then this goes on. And then eventually we get to P somewhere, like operation P. And then this has probability like P4. And so the probability to get to this state is the probabilities of each of the actions that are required to get to this state. In this case, it's P1 times P4. And then, so that's the probability of getting here. So, the idea with expected value is like, it's the sum of value, it's the sum over like, it's the sum over all outcomes of the value that you get from that outcome times the probability of getting that outcome. So for example, if one thing takes 3 operations and it has probability 0.1, then it contributes 0.3 to the expected value. It's 3 times 0.1. It's just like a formula. That's just what it's defined as. So here, how much does this contribute to the expected value? Well, it has length, it has like a sequence of length 2, and the probability of getting here is this. So therefore the contribution is 2 times P1, P4. So that's basically how we do the computations. We use the definition of expected value, we make this DFS stuff, like figuring out how the probabilities change, and then from there, eventually we have to stop whenever, or we have to not do an operation when it's like probability 0, or when our current probability is 0, we stop, because otherwise we'll go on infinitely. Because when the probability is 0, it of course contributes nothing to the answer, so there's no reason to consider it. So yeah, we do this again from the initial tree. We also try M, and then P is an ending state immediately. And every time we do a P operation, we add whatever the probabilities are times the length of the sequence to the answer. So if you wanted to verify that this works, the sample explanation is nice because it tells you the exact probabilities of everything. So you can verify that your DFS is correct by doing that, by like printing stuff and looking at that. So it's good for debugging. They were nice with the samples. So I got a wrong answer somehow. I guess it was precision issues, because it was like, it was using like epsilons and stuff. So eventually for, oh wow. Yeah, it gets wrong answer. Okay. That happened. Do other people FST too? Or is it just me? Seems like just me for the moment. That's pretty cool. D2 is running on tests. Alright, so that FSTs, that's awesome. Exciting. So what happened here? Was it still precision? Might just be precision. Maybe I could have capped the depth manually instead. I guess I could have made epsilon smaller. I don't know. That is a possibility. Could have made epsilon smaller. Can I see the test yet? No, probably not. Does my D1 pass at least? Okay, good. Why is D1... How is D1 slower than D2? It's the same problem, except my D2 does more work. So I guess that's precision. I don't really see how else it would be wrong. So that seems like it. You know, if I had not wasted like 40 minutes on C, and I just skipped C, went for D, went for E instead, then I probably would have gotten E. And that would have been amazing. And that would be like so much better off right now. But now I'm just stuck. So maybe there's some nice way to handle precision that like isn't stupid. I don't know. Or maybe there's some like I tried DP initially, it didn't seem like it would work just because the order of the operations kind of matters, but like maybe it also doesn't. I guess it kind of doesn't. Actually, I don't really know what I'm thinking. I guess it kind of just doesn't. So you can do some sort of like DP, and then it would work in like 20 squared. Maybe. Or maybe not. I don't know. I feel like it would though. You have. I feel like my initial idea would maybe work. You have the DP where the states are like the number of C operations you've done, the number of M operations you've done, and whether C is invalid yet and whether M is invalid yet. And then like transitions are like figuring out what the operation is and how it affects your values. And then for each state you add to the answer the probability of having P. Maybe that'll work? This run is a disaster for me. So that's just not happening. Okay, well anyway, I'm going to go over D1 and D2 separately, because D1 is like infinitely easier. In fact, I don't even know why they had the subtest. There was no reason to do that. It didn't really like add anything interesting. I don't think it was a good use of a subtask, but whatever, 3 points for people who skipped C and made the right decision to go for D instead. So, yeah, I think I should have made epsilon smaller. I think it would work, maybe, with that. I'll try it after the contest. The optimal original password is automatically decided by the adaptive interactor. Interesting. Okay, so we're doing n and k. Right. So in this problem, k equals 2. So essentially, what can you do? You want, suppose you just query like I equals 0. Suppose you like check each password independently. So you check, can the password be 0? Then can it be 1? Then can it be 2? Then can it be 3? Up to n minus 1, because you can make n queries. Right. So now with that, what does that do for us? Well, we can't exactly do this directly, because the password can change every time. So what we really want to ask is, suppose initially we asked if the password 0, and because the password hasn't changed yet, it's fine. But now maybe the password for 1 changed by something. And if so, we need to ask, we need to like figure out if the password was initially 1, after the operations we did, what would this become? And that's the number we need to ask, because we still need to like reverse engineer what we need to get to if the initial password was 1. So if we ask them a number that 1 would become after doing all the operations, then it would work for us. Yeah. And we do the same thing for 2. We ask the number that 2 would become after we've done all of our previous queries. Then for 3 and so on. The problem is this is n squared, naively, especially with like k, it's like n squared. It's like something stupid like n squared times log base k of n. So that's dumb. So we can't really do that. But for the special case of k equals 2, well, we're essentially asking x XOR in the when we change the value, when we have a value x, the password before was x, you guess y, then the password changes to z. So you want x XOR z is equal to y. The inverse of XOR is XOR. You can prove that with a truth table or something, or it's like intuition about how it works. So because the inverse of XOR is XOR, we inverse XOR x and we inverse XOR y, which is the same as XORing. So we basically just XOR on both sides. Z is equal to, in this case, I'm adding it on the left, even though it doesn't matter, because XOR is also commutative, so that works nice. So, but with matrices, for example, you have to do something called left applying, which is kind of fun. But because it's commutative, it's fine. It's like a weird operation, whatever. I'm just being explicit. So then z is equal to x XOR y, because x XOR x is equal to 0, because all the bits are the same. So every bit will return 0 as part of it. So z is equal to x XOR y. So really, what this changes by is this changes by 0. This changes by 0 XOR 1. This changes by 0 XOR 1 XOR whatever, or it changes by this changes by 0 XOR that. And this changes by 0 XOR our first guess XOR our second guess. And this changes by 0 XOR our first guess XOR our second guess XOR our third guess, and etc. Right? And so we can just keep a prefix XOR of that and then maintain it as we go along. There's also some sort of cancellations that's going on here that might make it easier, but I don't care. It doesn't matter. There's no reason to worry about cancellations because we can keep the prefix XOR as we go along, and then that gives us the exact value. We can query that and then continue on. I never went over my code for C. I feel like that's the most important thing. Well, actually, I don't know. It's stupid. You can read this on your own. It's like some DFS. It just simulates the moves. If you were to multiply everything by 200,000 to make everything integers, apparently that wasn't enough. I have no words. I think I should make this epsilon smaller. Yeah, I have no words. So, for D1, we're keeping this running XOR. So the code is extraordinarily simple. In fact, it only took me 3 minutes to do. It was basically easier than A. This was the problem I solved the fastest, which is stupid, because it's worth more than A also. I really don't know why they had this subtask. So you read an NK. Here you suppose K equals 2 just for D1. So yeah, X equals 0. For I up to N, we print I XOR this running XOR, and then this running XOR is XORed by the amount we queried last, which is I XOR X. In fact, I think it's always I, which is kind of funny. Wait. Is that true? Yeah. Huh, interesting. So you can always print X XOR X minus 1. And then that would work. Or I XOR I minus 1. 0 special case. And then that would work. It's kind of fun. In fact, the cancellation is a very big deal. Yeah, okay. Whatever. So, the point is, yeah. You can either maintain the running XOR or not be stupid and just do whatever. Anything works, it's fine. For D2, we use the same idea, except we sort of extend it a bit. So we're still figuring out what would happen. We're still asking, for this, what would happen, except now we're not using XOR. We're using, the K XOR, the weird operation they define. So we're figuring out what this would become after we did all these queries. So first things first, because the
the kitwise XOR is like done for each digit separately, for each kit separately. Kind of like these words actually. So the kitwise XOR is done like for each kit separately, and so the reason that's nice is because we can treat each kit like its own thing. So we can handle each kit independently. So for example, if we have like 3 kits, like 3, 2, and then 5, then we can like do the kitwise XOR for each kit independently and then treat them independently. So what I'm saying is, for these values, instead of storing what everything would become when it's like kitwise XORed with all of our previous queries. Also, this just becomes 0. All we would need to do is do it separately for each kit. So we store, for example, after 7 operations, for like the 3rd kit, or for the 0th kit, yeah, a lot of hyphens. We basically store a table for for example, say n equals 6, k equals 3. Then we have 2 kits, and everything's in base 3. So we store essentially 0, 1, 2. So after this many operations, 0 would, for example, become 2, and then 1 would become 0, and then 2 would become 1. And then this kit separately, we store that 0 would become this, not 3. 0 becomes 0, 1 become 2, 2 become 1, for example. And then to figure out the number that we need to query, we just construct it from this list. And then to update this list, well, basically, we're just figuring out this, like what 0 would become after this operation is whatever it would have become with the previous operations, plus whatever it becomes after this direct operation. So this is essentially the kitwise XOR, or like not the kitwise XOR, like the inverse kitwise XOR that they define. I love that word. Okay, yeah, I like this statement now. Problem's not that great, but I like the statement. So we do after this operation. So like this will become, for example, after this, like 0, 1, 2. And then we just maintain it as we go along. And then we construct the number. So the way we construct the number, it's a bit different, because the inverse kitwise XOR is no longer itself. So we want x kitwise XOR z is equal to y. Let's again look at each bit independently. Essentially, we want, for a specific kit, we want x plus z equals y mod k. So like congruence, essentially. So x plus z mod k is equal to y mod k. Right? Well, because we're working with modulo, there's a lot of modulo in this contest. Holy crap. There's A, B, and D now. So, yeah, brush up on your math, I guess. So now we can subtract x because we can just do that. So z is congruent to y mod. By the way, this congruence, it just says like modulo k, these two are equal. That's all this means. It's just like equality modulo k. So really, formally, we can like put a congruence with respect to k in there. That looks horrible. So z is equal to y minus x. But like that's it. That's it. Like it's whatever our queried value is minus what our previous value is. So if we, for example, here, we query the kitwise number like 2, 2, then this would just become, it would become 2 minus 2, 2 minus 0, and 2 minus 1. Say I do like 1, 2. And then this would become, similarly, it'd be 1 minus 0, 1 minus 2, and 1 minus 1. So negative numbers mod k is like, basically we just add k. So this becomes negative 1 plus k, which is 2. So we keep them within the range 0 to k minus 1. Okay, does pass, that's good. So essentially, this is what I'm doing in the code. I'm storing this what array, which basically asks, For this operation, what does this, so like, what xy basically says, what does the xth kit become if it started at y? So like if it was initially, what does the xth kit become when it initially started at value y? So like it's basically just this mapping. Then I'm taking the size, which is basically log base k of n minus 1. N minus 1 because the numbers don't actually include n, they're just from 0 to n minus 1. So now we initialize what. Initially, each what is just whatever it started as. And then here we construct the number. So for each kit independently, we're going to guess I. So we know we want to ask, if the password was initially I, what would it be now? That's the number we ask. So to use the what array, we take this kit of I, and then we query the what array to ask like what it would be now. And then we set that kit in our number. And then we do that for each thing. Then we just ask that, do the query, and then now we're reconstructing the what array. So for each kit independently, we're just setting it to that. We're just setting its what array to the updated value, which is the kit at that guess minus whatever the what value was initially, or before, not initially. And then to do like a minus b mod k, it might help to like, you can do, C++ is weird, like a negative value mod something can still be negative. So to remedy that, you can do like add k here, and then that way it'll always be positive, because b is between 0 and k. So then this will always be positive. So then the whole thing will be positive. And also I'm not doing explicit mod. You can do like, if a and b are both small enough, if a and b are both in this range, then you can essentially say take a plus b, and then if it's greater than k, subtract k from it. Because like basically a and b are between 0 and k. So a plus b is between 0 and 2k minus 1, but whatever. So either it's in like 0 to k minus 1, in which case we don't have to do anything, or it's in k to 2k minus 1, in which case we have to subtract k. And like either way that works. So basically, subtraction is a lot faster than modulo. So that's why we're doing this. Because it could be like the constant factor that matters. Because this is technically like, I guess it's not the worst. Actually, it shouldn't be that bad. But I'm just saving time. It's just like a little trick you can do for modulo problems. And we do it for each kit independently. And yeah, those are the problems I solved minus C apparently. So this is just gonna be a train wreck. Yeah. Anyone else have FST? Am I like alone in this? Oh my god. Of course, if if someone would be the one to FST C while doing it officially, it would be him. Of course, it would be him. There's no way it wouldn't be him. So yeah, skipping C was the move, and going for E and getting way more points. Like seriously, so many more points. Imagine how many more points I could have. It'd be like a lot of points. A lot of points. Cool. So that leaves E. And so by looking at some of the solutions of people on my friends list, I figured out what the solution is. I don't have a proof for it or anything, so I can't like justify it that well, but I can just present what it is and like explain it. So we have a permutation. We need to turn that permutation into a hypercube. So let's start by just constructing the permutation and like constructing the hypercube itself. So we start with 0. Because the permutation can be anything, assume index 0 is actually 0 in the permutation. Now, what's going to be adjacent to 0? Or in particular, what's going to be index 1? And it can really be anything that's adjacent to 0. So we pick something that's adjacent to 0. And we say, look, you're 1 now. So this is 0, this is 1. So now, what about 2? What about 3? Essentially what we want to do now is we want to find some other edge, and then we're going to say this is 2, this is 3, and then we're going to merge these hypercubes into a larger one. So here we have a 1D hypercube, and we have another 1D hypercube, and then we're going to merge these two into a 2D hypercube. So we basically just need to find another 1D hypercube that corresponds to this one. So that in particular, this 2 has an edge with 0, this 1 has an edge with 3. So how do we do that? Well, we're essentially mandating we need this edge from 0. So let's construct this right away. So this vertex is going to be 2. Then we can only pick vertices that A are adjacent to 2 and B are adjacent to 1. So one way to find this is just to like it's sort of like a cube, but it's also not. Essentially, I say when I visit a vertex, or like for each vertex, you store the minimum adjacent thing. Actually, no, there's a better way to think, there's an easier way to think about it, but it's not entirely correct, and I'll show you why later. But essentially, we're storing like the set of the visited nodes we have, and then here, any node we pick must be adjacent to 2 of them, so it must have 2 adjacencies to the purple set. So we pick a node that's adjacent to 2 of them, and then we do it like this. And so this is node 3 now, because it corresponds to 1. So we pick nodes that work for adjacencies. Then move this a bit down. Now we need to construct the next layer. So we need a 2-dimensional hypercube that corresponds to this. So we must find some set of 4 nodes such that this node has an edge to 0, this node has an edge to 2, this node has an edge to 1, and this node has an edge to 3. And how do we do that? Well, let's once again start from 0. Then now we're tasked with creating a 2D hypercube sort of like rooted at this node, and so that it corresponds to this one. And so in particular, we need to find the next node will correspond to 1. So we need any node adjacent to both this and 1. So all I did was I just store for each node, like, I don't know, like the lowest value. Store for each v, like the lowest adjacent node. Like the value of the lowest adjacent node, or the lowest value of the adjacent node. So for example, like this vertex that's adjacent to 1 but not to 0 would be, its low value would be 1. Because it's just like, it's the minimum value of the of all of its adjacent nodes. Except there's also like, we have to specifically use the indices in the non-permuted hypercube. Like the normal, like we're saying this is vertex 0 in our hypercube, this is vertex 1. It's not the indices themselves, it's like the values of the hypercube we're constructing. So it's like the unpermuted hypercube. So if we do it like that, then the value with low v is equal to 1 and adjacent to 4 will be the one that corresponds to 1. Because it's adjacent to 1 and it's adjacent to 4, so it has to correspond to 1. So we do this. So now this value is 5. We continue. Now we look for 6. So now within this task of constructing a 2D hypercube, now we're tasked with finding a 1D hypercube that corresponds to this and this. But it turns out it's enough to correspond only to this, because it's fine, because this already corresponds to this, and so this only needs to correspond to this, because then it will automatically correspond to this because symmetry. So that's why low V is enough, because we only need to correspond to the biggest hypercube that we have so far, or the one that's sort of rooted at 0. So here we look through the adjacencies of 4. We find something such that its low value is equal to 2. And then if we were constructing a 3D, then we would look for something with the low value of 4, and so on. And the way to do this nicely is for this vertex, we sort its edges with the comparator as the low value. And then that works because it'll process the lowest node first, and then the next lowest, and then the next lowest, and so on. And also because of the way the hypercube is nicely arranged, it works out that way. So you just sort when you get to visiting a node, you sort its adjacencies by their low value. Also, low of V is infinity if it hasn't visited anything yet. Yeah. So we look at the neighbor of this, we find the thing that corresponds to 2. Or in particular, the largest thing that hasn't been corresponded to yet, or the smallest thing that hasn't been corresponded to yet of our initial hypercube. This is 6. Now, again, we're tasked with building a 0-dimensional hypercube that corresponds to this. In this case, it's anything. So this works, and it has to correspond to 3. And then we would continue from here. Now we would build this edge, and then if we had more n, then we would build a 4-dimensional hypercube by constructing a 3-dimensional hypercube such that it corresponds to this one, and all the low values work out. But I can't draw 4D, so we're going to stop here. But yeah, that is the idea. And then this gives us, if this was initially, say its permutation value is 5 or something, and this was initially 0, then it tells us that, it lets us do the mapping. It says that the node in the permuted hypercube with index 5 has, initial hypercube index 0. So therefore, wait. Going in order. I think this might actually be wrong too. Okay, whatever. Going in order. This essentially just means no, I don't know what going in order is. I don't know what I'm saying. But essentially it means that the value with index 0, or it means index 0 in the unpermuted hypercube corresponds to index 5. So you can use this to restore the mapping, and this gives you the permutation. So now, how do we do the coloring? And this is the part that I didn't solve, and probably the reason I got the wrong answer. Essentially the way it works is if n is a this is all unproven. If n is a power of 2, then it's okay. Else, there's no coloring. And the way we construct the coloring is essentially we look at each node of the hypercube. Or in particular, we look at the original index of the node. Like, we need to work with a hypercube that's, like, nice and power of 2e. So, like, the unpermuted hypercube. And the way we color it is, like, and then when we get the colors of the original hypercube, we can use the mapping again to, like, figure out the colors in the permuted one. So that works out fine. Yeah, okay. It works that way, right? Wait. Now I'm, like, super confused. Again, as always. We're just, like, we're doing the mapping. It's like this. So permutation is, this maps 0 to 5. We're looking at this index. And we're saying 0 is mapped here. Mapping 0 to 5. Alright, I guess that makes sense. Okay. Yeah, okay. So the way, I don't have proof for this, but you can show that the construction works for this. So basically you convert each number x in the unpermuted hypercube to its, like, bitwise form. So for example, suppose n equals 4, then every number is a 4-bit number. So, like, for example, suppose n equals 4, and we're working with v equals, like, 13. Then in binary, it's 1, 1, 0, 1. Then the color we give it is, like, for each bit, we assign to it the position of its bit. So this is bit 0, this is bit 1, this is bit 2, and this is bit 3. And then the color we give it is the XOR of the on bits, of, like, the bits that are 1s. Like, the XOR values for each bit that's 1. So for example here, this has value, this has 1 here, it has 1 here, and it has 1 here. So this gets the color of 3 XOR 2 XOR 0. And then, like, this works because, like, because of the way the hypercubes work, like, there's an edge between x and y, if and only if x and y differ in exactly 1 bit. So for example, x would be like 0, 0, 1, 0, and y would be like 0, 1, 1, 0. So we look at the bit that differs, and then, like, essentially with this construction, x will have every color next to it because, like, for example, for n equals 4, we're considering the 4 adjacencies to x. So suppose, like, this is the one that differs in, how do I notate this? So, like, this is x. This is, like, it differs in the first bit. It differs, this one differs in the second bit, this one differs in the third bit, and this one differs in the fourth bit, like D for differ. Right? So, because XOR is, like, it's like 1-to-1, it's like a bijection. For every input, there's a unique output. So, like, this is whatever, this is, like, color of x, XORed with 0. This is the color of x, XORed with 1. This is the color of x, XORed with 2. And this is the color of x, XORed with 3. Now, because XOR is 1-to-1, that means all of these numbers are different, which means that x is adjacent to all different colors. So the coloring works. And And the same thing doesn't work for n being not a power of 2, just because like the construction doesn't work because some things are like not the same. Or in particular, you might end up with colors that aren't in the range 0 to n minus 1. Like, for example, with 5, you can get like 3x or 4, which is 7, and 7 is too big. So it doesn't work. This specific coloring doesn't work. There's probably some argument that shows that no coloring works, but I don't know it, so yeah, that's all I got for this. So essentially, this is the answer. It is an answer that got accepted by people, so I'm guessing it's fine. Yeah, anyway, this happened. I'll try a larger epsilon and then see if that works, and then I'll like talk about it in comments or whatever with my usual. There's always some update that I have to do in the comments just because like some random stuff happens with the contest, so I don't know. Maybe something else will happen. Maybe I'll like retroactively get hacked on A or whatever. Who knows? I mean, the A and B were pretty quick, so I guess it's fine. How's their room? Yeah, this is horrible. Now someone else FST C. Or answer on test 4. Or answer on test 5. Ooh, got farther. Still can't see the tests. How long did this take? It was like 50 minutes, so it'd be 1,000 points. Maybe like 1,200. Maybe like 1,100, so 39. Okay, not that great. Anyway, should have gone to D instead and just like skip C entirely and done this. I don't know. I could have figured out the way to guess the coloring, and then that'd be fine to guess that it always works. But I had nothing more. That was that. Anyway, that's cool. Yeah, can't do well every day. This was very different, but yeah. Okay. Yeah, goodbye.